Hi, I want to give a quick overview of the consensus problem that must be solved to maintain blockchains in a synchronized state. So here I'm showing two blockchains that are not synchronized, that they've chosen different blocks. And so we have this consensus problem of how do we arrange so that even in an asynchronous network where the only means of communication is by sending messages that may or may not be delayed, how do we ensure that we can drive consensus? So that's the problem. And it's used in driving consensus in what we call Byzantine fault-tolerant algorithms, where some of our messages may be false. So the general approach to this is that we choose a number of leaders at random. So we have, and this is used in Hyperledger, for example, in permissioned blockchains, but it can also be extended to non-permissioned blockchains, as with Algorand, Professor Silvio Micali's quite brilliant algorithm, and I'll describe that a little later. But in general, what we want to do is, out of the nodes in network, for example, say an Ethereum network, we choose a number of leader nodes, and we can do this based on how much stake they have in, how much ether they have, for example, which would be proof of stake, or by some other means. But here, let's just assume these are all equal participants, weighted equally. We can extend it to different weights quite easily. So now we've got a number of leaders. In the algorithm by Micali, and also in one called Gossig, we order these leaders. So I'll describe exactly how that works later, but let's suppose we have some ordering. So leader number one is the most important. If they're not responsive, then we're going to take leaders number two suggestion and leader number three, etc. And we can have enough leaders that we know we'll get some response from the leaders, even if other people are not on the network at the moment. So this process of choosing leaders out of the community is called solicitation. And so the general approach is that the leaders broadcast their choice of block and their leadership status. And it's a question of how do we know who's leader number one, etc. And we'll come back to that. But the idea is, based on these leaders' messages, in the next round, the leaders, so these leaders they choose a block and they broadcast it out, and then they cease to be leaders. So there's only one broadcast they ever make. So it's very difficult to attack them, because by the time you know that they're a leader, then actually not a leader anymore. So now round two, we've got new leaders, and the rule is that they will always broadcast out the block that the leader, the highest level leader, if you like, leader number one from the last round, sent out. So now these people broadcast out, they have some consensus and broadcast out a block that everyone agrees on. So now, how does this saltition work? Well, what we're going to do is we're going to take some shared secret. So this mustn't be a secret that maintains constant. We need it to change with every block. So what we're going to do is we're going to choose Q, the hash of the last block. So whatever the block was, we're going to take its hash. It's actually embedded in the last block. So we'll take this Q, and now we're going to have certain rounds in drive towards consensus. So round one, R is 1, and Q, both Alice and Bob can look up Q from the last block added to the blockchain. So they can calculate now the hash of Q plus R, without communicating at all. So both Bob and Alice know the hash of Q plus R, but they don't know if they're leaders yet. Now, the leadership score is derived by they need to sign the hash of Q plus R with their private key and then take a hash of that. And the person with the lowest hash is going to be leader number 1, the next lowest is going to be leader number 2, etc. Now, what happens is that to prove Alice's status as a leader, she's going to broadcast out, so send to Bob, for example, in this instance, the hash of Q plus R. And she's going to sign that with her private key. So she's sending out a signed version of the hash of Q plus R. Now, Bob can take the hash of the signed version, Alice's signed version of Q plus R. So Bob can both calculate her leader status, so he gets the value 89FC, the same one that Alice did. But furthermore, he can decrypt the signed version and retrieve Q plus R, which he already knew. And so he knows that Alice hasn't cheated because he gets the same hash of Q plus R that he did. So Alice's hash of Q plus R is the same as his, so she didn't cheat. And he knows Alice signed with the private key because he can decrypt. So this is a zero knowledge proof. Alice has proved to Bob her status without revealing her private key. So this is a really amazing algorithm, and I believe it's going to be adopted by many of the blockchains. Okay, I hope you enjoyed this.